Welcome to Chapter 4. This is our fourth little video that we have. We're going to talk a little bit today about some of the elements of surveying and how they relate to cadastral mapping. So to start off, we're going to talk a little bit about how the state of Utah is originally surveyed. The state of Utah is plotted into a grid of squares 6 miles wide by 6 miles long called townships, and those townships are determined from an initial starting point. Most of the state is on the Salt Lake Basin Meridian. There are sections that are in the Uinta Meridian, but most of the state works off of the Salt Lake Basin Meridian. So those townships are determined from that initial point in downtown Salt Lake. So the north and south line is called the meridian, and the east and west line is called the baseline. So working along the principal meridian line and the baseline, the townships are set at 6 mile intervals. And then by extension, the townships are marked off into grids within each township, or 36 square miles, and those are called sections. And they can be, and those townships are labeled based on their relationship to that center point. So Township 9 North, Range 2 West is 9 townships north and 2 townships west of that very central point. So like I said, those townships are further divided into sections, and those sections are each 1 square mile. Those sections contain 640 acres, and individual sections are numbered kind of in a weird way. You should know how to number a section if you don't already, but it starts in the northeast corner and goes 1, 2, 3, 4, 5, 6, and then it drops below it 7, 8, 9, 10, 11, 12, drops down 13. So it goes in an S-shaped pattern, but it starts at the northeast corner and ends in the southeast corner. Going 6 miles each way. So you'll need to know how to do that for sure. That's very important in cadastral mapping, is understanding which section and what the neighboring sections are. You'll also need to know how to explain what the breakdown of the sections are. If you see in your book on page 4-2, you can see the breakdown of the sections. You can see that the northwest quarter of the northwest quarter is a 40-acre piece, or just the northeast quarter, the east half of the southeast quarter. Be able to understand how those are described. Both of those items will probably be on the test. But sections can be broken down into those pieces into quarters, or sixteenths, which are a quarter of quarters. But they are also we mentioned every 6 miles. Every 6 townships there is adjustments, and actually each township has adjustments for some sections. The example is section 7 here. So on the north side of the township and on the west side of the township, those sections all have lots that adjust for the curvature of the earth, and they can either be short or long based on to make up for, like I said, that curvature. So an example of that section 7, you can see lot 1, lot 2, lot 3, and lot 4. Those are all small portions represented here. Sometimes they're larger, sometimes they're smaller, sometimes they're pretty close. But those go on. We mentioned adjusting for the curvature and those lots, and so all of the north south township lines are true meridians, so they're longitude lines, and all the east and west township lines are latitude lines. Because of the way the Earth is shaped, those lines point towards the North Pole, so as we get closer they actually arc together, and so this difference is compensated. This is important to know. The difference is compensated by establishing section lots, irregularly sized fractions of sections along the west side of the township, and along the north side of the township. That's important to know. So, and those create those lots sometimes. So also other things that can create lots. Sometimes there might be rivers that go through an area, and so they might have platted out lots, or a lake. Sometimes around patented mining claims, they might do lots, as you can see some of them in your book. Also, if they deal with unsurveyed land, oftentimes there's lots around those. And also when we deal with those compensations, sometimes there's large oversized sections, and you can see that. So we talk about a quadrangle. A quadrangle is actually 24 miles square and consists of 16 townships. And because of that, the corners don't always line up. Sometimes you'll have offset corners for section lines because of that curvature and that adjustment. So be aware which corner your description is actually calling from, because sometimes those might be offset. So let's talk a little bit about how a section is broken down into different parts, and kind of label what those parts are. So first off, we know what the corners are because we're dealing with a section. It's square, so we have corners, and the corners of the square are based on the compass. So you have your northeast corner, your southeast corner, southwest, and northwest corner. Now in between those we have what's called quarter corners. So if we broke the section up into quarters, they would each have a quarter, and so it's where those quarter sections meet. So we have the north quarter corner, which is the corner between the northeast and the northwest. You have the east quarter corner, the southwest quarter corner, and we also have 16th corners. Now those 16th corners lie between the quarter corners and the section corners. And then actually, if you connect the dots, there's a bunch of them. There's also another major corner that might be used frequently, and that's the center of the section. It's actually the hardest to find and to lay out, but because it requires you to know where all of the others are. But you can see some of those layouts and as we get more detailed there in your book. But you can see that, for example, on page 4-6, you have that section and all the 16th corners, the bearings and the distances between those. So you could actually call to any of those section corners because if it were laid out like this, you'd be able to know what those are. So oftentimes the surveyor's office will have corner tie sheets. So where that relates to the corners that we deal with in legal descriptions and where they physically lie on the ground. Those tie sheets usually depict where, and they might have a drawing or an air photo of exactly where that is in relation to some of the surrounding landmarks. Also, there's usually ties to different things, telephone poles, fence posts, things like that, the bearings and distances between those, so that if anything ever happens to those corners, they can be found again. So all of those corners are done like that. So, and like I said, those are section corner tie sheets or data sheets. Most government surveys show quarter sections and sections that measure exactly 2640 and full sections that show 5,280 feet with 90 and 180 angles. But most sections aren't actually like that. They vary, and which causes our office quite a bit of problems. Because there's not an exact mile between them, and oftentimes our ownership plat maps deal with a perfect square. We have to deal with some of those things when mapping out the property descriptions. We need to know what those distances are and what those measured bearings and distances are, so that we can accurately map those for taxing purposes without showing overlaps or gaps and things like that. So so all of the monuments in the whole system are actually mathematically related to each other, and that's the use of the state plane, the coordinate system that we use. But let's talk about some of the basic facts about the Utah State coordinate system. So in your book, it gives you kind of an example of what happens. And most maps of the United States and of the globe are very difficult, and they showed skewed things. You may have learned in school about Greenland, how it can show up giant and huge on a map, but it's not actually. It's because they've taken it and they've kind of adjusted the thing. You can kind of see the picture here of the trying to take a round object and make it flat.
Let's start.
Wait, I want to see this.
This is Josh Lyman.
Indeed you are.
Josh, this is Dr. Fallow, and
Hi.
who's Mary Men.
Yes.
Should we begin?
Yes. Plain and simple, we'd like President Bartlett to aggressively support legislation that would make it mandatory for every public school in America to teach geography using the Peters projection map instead of the traditional Mercator.
Give me $200 and it's done.
Really?
No. Why are we changing maps?
Because, CJ, the Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
The German cartographer, Mercator, originally designed this map in 1569 as a navigational tool for European sailors.
The map enlarges areas at the poles to create straight lines of constant bearing or geographic direction.
So it makes it easier to cross an ocean.
But
Yes.
it distorts the relative size of nations and continents.
Are you saying the map is wrong?
Oh dear, yes. Look at Greenland.
Okay.
Now look at Africa.
Okay.
The two land masses appear to be roughly the same size.
Yes.
Would it blow your mind if I told you that Africa is in reality 14 times larger?
Yes?
Here we have Europe, drawn considerably larger than South America. When it's 6.9 million square miles, South America is almost double the size of Europe's 3.8 million.
Alaska appears 3 times as large as Mexico, when Mexico is larger by 0.1 million square miles.
Germany appears in the middle of the map when it's in the northernmost quarter of the Earth.
Wait. Relative size is one thing, but you're telling me that Germany isn't where we think it is?
Nothing's where you think it is.
Where is it?
I'm glad you asked. The Peters projection.
It has fidelity of axis.
Fidelity of position.
East-west lines are parallel and intersect north-south axes at right angles.
What the hell is that?
It's where you've been living this whole time. Should we continue?
Uh-huh.
So we deal with some of those things, and that's where we get some of the errors. The next page you can see it's very detailed, but it's an example of the state plane coordinate system and existing monuments there for Utah County. You can see all the bearings and distances for the section in the whole township, and all the relation to the points and things like that. And so some of those things, those principles that we use for surveying, we definitely use in the recorder's office because of the legal descriptions. They all tie to those things. But surveys also are more accurate than just legal descriptions. And there's different levels of accuracy. When you have your GPS unit that you have in your phone or in your car, the accuracy is just a generalized location. Sometimes you may have looked to see where you're at, and it shows like a big circle where you're at, because it doesn't know exactly where that at, and they call those orders of magnitude. And so those standards are set up so you have first order accuracy, second order accuracy, or third order accuracy, and those accuracies are defined in your book there for what they are. But the first order accuracy is actually, you can see it's 1 part in 25,000 parts or better. And so that's the highest accuracy. Second accuracy is 10,000 parts or better, and third order is less than 10,000. As mappers, we can locate points on the map and points on the lines on the computer through calculations within very small measurements, and in order on the map this accuracy. But mappers don't have the constraints and challenges that surveyors have in the real world. So the important thing to know is that we get all of the surveyors' work as they file them. Many of our offices are combined, or we deal with a lot of those surveys. But a very important thing that you'll if you haven't realized this already, you should realize soon, is that no two properties that are surveyed will match up exactly. It just won't happen. They can be surveyed by the same surveyor. It could be 2 months later. It could be two different surveyors on the same day. They just won't ever match up perfectly. It's nice if they do. Oftentimes they'll reference each other and say, hey, this is what I got, this is what was found previously, but those surveys won't ever match. But the difference may be very small, but they won't always match up perfectly. So surveying largely has changed over the time. They used to survey looking through scopes and having a person stand there, and they measure the distance between those and what and some of those measurements and things like that. They've done the original Utah system that we talked about. The section, township, and ranges were laid out by people pulling chains and doing that. They had big survey system, and it's actually quite amazing how a lot of that happened with the technology that they had. They didn't have any technology. They had these big things, and and two guys walking, pulling a chain, and they'd stick things in the ground, and and it's just amazing that they got as accurate as they did. That they're mostly straight lines, and so, but technology has changed, and so now we don't have those big measuring things. We don't have the chains, and we don't have pulling things around. We have the GPS. But let's talk a little bit about how GPS works, so you can understand the biggest difference between how accurate. We talked a little bit about accuracy. How accurate is how many satellites and things like that they talk about. So GPS actually is an acronym. It stands for a Global Positioning System. So it's kind of interesting how the whole GPS thing works. I've done a lot of research on this. It's been interesting to see that, because when we were updating the manual, a lot of this stuff has been updated and changed. So I want to make sure you guys had the most updated information. But when people usually talk about GPS, they're usually talking about the receiver, the thing in their phone, or where their position is. But it's actually much more than that. It consists of receivers, but those receivers have to talk to something, and they're talking to satellites placed around the Earth. So originally, there were 27 satellites, 24 of them were in operation, and they had 3 extra in case one of those failed. And it's actually the military that developed that for precision things. And as they got more people and more funding for it, the Department of Defense launched those, and they each of those satellites are actually solar powered, and they circle the globe at about 12,000 miles per hour. So they're going pretty fast, but they're out there, so it their orbits are pretty ranged. So there's 6 basic orbits that these satellites are in, and some satellites are on the same orbit. But the idea is that multiple satellites would be visible any place on the Earth. So based on that, and if you had several of them, you could be able to tell where you were at based on that. So that all 24 hours a day, they could do it. And that was originally started in 1994 when the Defense Department launched those. Since 1994, GPS has been when the original satellites were launched by the Department of Defense. GPS units have been more commonplace, and additional receivers have been put up. Newer satellites have been launched into orbit, replacing most of those original 27 satellites. And the GPS constellation, so all the satellites are up there, are a mix of new satellites and old satellites, and stuff, as they've launched new ones and retired some of the old ones. But as of December 11th, 2015, there were 31 operational satellites in the GPS constellation. And that doesn't include all the extras that are up there. They're decommissioned satellites, but they're still in orbit. They're just not being used, but they're still there in case they have to reactivate them for some reason. So even though GPS was originally created as a device for navigation for the military, it's used actually outside the military, and it's mushrooming. They're becoming small enough and cheap enough that they're carried in just about every application, in most facilities. They're used in farming, all sorts of different things, in cellular phones, backpacks, outdoor vehicles, automobiles, cars, and so a lot of them have that information. So the GPS space part of the GPS system consists of a constellation of satellites that are transmitting radio signals to the users who have those receivers. They receive those, and that's how they communicate. and the United States is committed to maintaining their availability at least 24 operational GPS satellites 95% of the time. If you want more information about those, you can go to http://www.gps.gov. That's where I got a lot of the information. There's a lot of things on there. I actually got to see a launch video of the last December 11th, 2015. I got to see the launch of that on there. They have that posted there. Anyway, a bunch of cool things. But continuing on, talking a little bit about how it works. So we talked a little bit about those GPS receivers and those becoming commonplace. And those what they do is they exchange the information with the satellites. So if the receiver can receive signals from unobstructed or direct line with those satellites, meaning you're not inside a house or you're not in a car, sometimes it has difficulty in a car, things like that, or under a tree next to a building. Sometimes those are hard to get satellites because they're obstructed. But if it can connect to at least 4 satellites, it can determine the location. And this is something that you'll need to know for the test. But in order to make a simple location calculation, the GPS receiver has to know 2 things. Okay. Number 1, it has to know the location of at least 4 satellites that are in the sky, and the distance between those satellites and the GPS receiver that's on the ground. And so you can see kind of a picture there. It knows the distance, and it triangulates the space right there between those. It's on page 4-15. You can see those satellites. Also on that page you have pictures of what the satellites actually look like. Some of the older one and some of the newer ones. But surveyors use multiple GPS receivers in order to increase their accuracy. So they deal with things such as changes in the atmosphere, radio wave interference, things like that from satellites. And so in order to get a better accuracy, they actually use a stationary base station. So they set up that base station on a section corner or a known point that they know, and so then they'll go out and they'll have a rover, and so both of those are constantly communicating with the satellites, and the rover, the one that they're actually measuring points with, that's mobile, that one connects to the satellites and also connects to the base station, and so therefore it knows where it's at with those 4 satellites and the base station knows where it's at based on multiple satellites. And so because of that, it just adds an extra triangulation, and you get a much more accurate location because of that. But those have issues with that takes out some of the issues that it have with radio waves and other interference because there's multiple things there. So on the very last page of the surveying, we can see some of the survey equipment that we have. You can see the survey controller. That's what talks to everything. The base station is just a simple tripod with a GPS receiver on the top. It usually has a battery pack and a data logger that just logs all the data. The rover is usually on a tall pole, and it can either have legs to help stabilize it for some of the longer shots, or you can hold it for some of the quick shots. But there's quite a bit of advantages over using GPS equipment over some of the surveying equipment. One of the big advantages is you can have a 1-person survey crew. So before, where you had to have at least 2 people, sometimes 3, one person can go set up the base station and then the rover. They actually have, the state of Utah actually has a set of base stations that are that are constantly sending out the location. So oftentimes you don't even need to set up a base station. You can just use a wireless connection, and you can take your rover out, connect to those existing ones that are on all the time, to save a step, but they still have that communication. But you can do it with a one-person crew now, and so because of that, you can get more surveys done and quicker. Also, you don't have to be in sight of a survey monument, where before you had to shoot it or do that. The radio signals can go quite a bit. You can have buildings in between your base station and you, and it just knows that. The other thing you don't have to is you don't have to walk from one point to to there from the section corner. If you know where the section corner is because your base station's up, you can just go and shoot the corners, and then you know where that is. You can survey in stormy or foggy weather. You can survey at night, because you don't have to be able to see. You just have to see the screen. The accuracy is improved. Completing a survey is much faster because we've taken out a lot of that time. The other thing is that surveying will often give you the Z-axis. So it'll give you an elevation, and you can know that as long as you're northing and easting, or east and west coordinates, and north and south coordinates. So a lot of that. So that's kind of a quick review of what the surveying is. Check out the homework. Do that. We'll meet and have our discussion this week. And if you've got any questions about surveying or anything, shoot me an email. Let me know. We can surely answer any of your questions about either the equipment, about section corners, about how they're all set up, things like that. All right. Thanks. Bye.